Welcome, everyone. I'm excited to kick off our presentation today. Today, we're diving into the fascinating world of ratios and proportions. This is the first slide, and it's our cover slide, so I just want to give you a quick overview. We'll explore what ratios and proportions are, why they matter, and how they can be used in real-life situations. So, let's get started and make this an engaging and insightful session. Let's take a look at the contents of this presentation. Starting with the outline, we see that the first topic is what is a ratio, which is fundamental to understanding the rest of the material. Then, we move on to how to use ratios. This is about applying what we know in practical situations. Next, we explore how to simplify ratios, a key skill to make ratios easier to work with. Further along, we have more examples, because practice makes perfect. The presentation also covers properties of a proportion, helping us understand the relationships between ratios that are equal. We will see now on to proportions, which connects ratios to proportions, showing how they relate. Later, there's, can you solve this one? And now you know enough about properties, let's solve the mysterious problems, encouraging you to apply what you've learned. We also have sections dedicated to properties of proportions and examples to deepen your understanding. Finally, the presentation wraps up with questions like, so what do you think? To engage you in reflecting on the concepts. Throughout, the focus is on simplifying ratios and understanding proportions, which are essential skills in math. This structure is designed to guide you step by step from basic ideas to more complex problems, ensuring a comprehensive grasp of ratios and proportions. Let's take a closer look at the outline for today's discussion. First, we have mysterious problems. These are challenges that often seem puzzling or hard to understand at first glance. They can be complex issues that don't have straightforward solutions. Throughout this presentation, we'll explore these problems, try to uncover their underlying causes, and look at ways to approach them more effectively. By addressing these mysterious problems, we can develop better strategies and insights. This ties directly into our overall theme of problem-solving and innovation, showing how understanding complexity can lead to smarter solutions. So, keep this idea in mind as we go through the details. These problems might be complex, but they're also opportunities for growth and discovery. All right, let's dive into the outline for today. First up, we have ratios. So what exactly is a ratio? Well, a ratio is simply a way to compare two quantities, showing how much of one thing there is relative to another. It helps us understand the relationship between these quantities. Next, we'll look at how to use ratios, like in real-world situations, whether it's cooking, mixing, or analyzing data. We'll also cover how to simplify ratios, because often, the ratios we start with can be made more manageable by reducing them to their simplest form. Then, moving on to proportions. A proportion is basically an equation that states two ratios are equal. It's a powerful concept because it allows us to solve for unknown values when the ratios are related. We'll explore the properties of proportions, like what makes a proportion valid and how the cross-multiplication works. Finally, we'll discuss how to use proportions in various problems, connecting this concept to practical applications and showing how it fits into the bigger picture of understanding relationships between quantities. Throughout this presentation, keep in mind that both ratios and proportions are fundamental tools for comparing quantities and solving problems efficiently. They help us see the bigger picture and make informed decisions. So let's talk about what a ratio really is. Essentially, a ratio is just a way to compare two numbers. It shows us how much of one thing there is compared to another. Now, you'll notice that ratios can be written in a few different ways. The first way is using the words a to b, which is a very natural way to think about a ratio. The second way is with a colon, like a b. Both of these are common and easy to understand. Since a ratio is like a fraction, it's important to remember that the second number, or b, cannot be 0, because dividing by 0 is undefined. Also, when we write ratios, we want them in their simplest form, meaning we reduce them to the smallest numbers possible without changing their value. This makes the comparison clearer and easier to interpret. Understanding ratios is fundamental because it ties into many other concepts in math and real-world applications, helping us compare quantities effectively. All right, let's talk about how to use ratios. On this slide, I want to point out that the ratio of the length and width of this rectangle is 4:1. So, if I tell you that one side is 4 centimeters, the other side must be 1 centimeter, maintaining that 4:1 ratio. Now, what happens if the rectangle is scaled up to 8 centimeters long and 2 centimeters wide? The ratio still remains 4:1 because for every 4 centimeters of length, there's 1 centimeter of width. It's a consistent relationship, regardless of size. Next, I want to mention the ratio of cats to dogs at my home, which is 2:1. But here's a tricky part. If someone asks how many dogs and cats I have, I can't give exact numbers just from that ratio alone. What I do know is that if a fight broke out, each dog would have to fight 2 cats, because the ratio is 2 cats for every 1 dog. Finally, let's look at the ratio of boys to girls in a class, which is 12:11. This means that for every 12 boys, there are 11 girls. But it's important to understand that this ratio can represent many different possible total numbers. It could be just 12 boys and 11 girls, or it could be 24 boys and 22 girls, or even 120 boys and 110 girls, showing that ratios help us understand the relationship between groups, no matter the total size. So overall, ratios are a way to compare quantities, and they stay consistent even when the actual numbers change. They're a powerful tool to understand relationships in many different situations. Now, let's talk about how to simplify ratios. On the last slide, we saw some ratios that were already simplified. So how do we do that? Suppose we have a ratio of boys to girls in the class. To simplify it, we find the greatest common divisor of the numbers and divide both parts by that number. Similarly, for the ratio of the length and width of a rectangle, we do the same process. For example, if the ratio of cats to dogs in my house is 4:8, I can simplify it by dividing both numbers by 4, which gives me 1:2. Ratios can also be written as fractions. This is really useful because it allows us to do math with ratios, like adding or comparing them. So, understanding how to simplify ratios makes working with them much easier and helps us see the relationships more clearly. All right, let's talk about how to simplify ratios. Imagine I tell you I have 12 cats and 6 dogs. The question is, can we simplify this ratio of cats to dogs to a more manageable form, like 2:1? The key idea here is to find the greatest common factor, or GCF, of the two numbers. In this case, the GCF of 12 and 6 is 6. Now, to simplify the ratio, we divide both numbers by that GCF. So, 12 divided by 6 gives us 2, and 6 divided by 6 gives us 1. That means the simplified ratio of cats to dogs is 2:1. This process is really useful because it helps us see the relationship between quantities more clearly and makes comparisons much easier. Remember, always look for the GCF to simplify ratios efficiently. This concept ties back to our overall theme of making complex numbers easier to understand through simplification. Now, let's look at how to simplify ratios. Imagine a person whose arm is 80 centimeters long and who is 2 meters tall. Our goal is to find the ratio of his arm length to his total height. To do this accurately, we need both measurements in the same units. This is a key step because ratios compare quantities directly, and having different units can make that tricky. So let's try converting everything into centimeters first. Once both measurements are in centimeters, simplifying the ratio becomes straightforward. This process highlights an important concept: converting units to compare measures effectively, which is essential in many real-world situations and throughout our study of ratios. Now, let's see how we can simplify ratios. When we have the same units, they often simplify nicely to 1. To make both numbers into integers, we multiply both the numerator and the denominator by 10. This way, we're able to keep the ratio equivalent but easier to work with, especially when comparing or simplifying further. Remember, the key idea is to make the numbers comparable by having the same units and converting them into whole numbers. This approach makes the process of simplifying ratios much more straightforward and connects to our overall goal of understanding ratios in a clear, manageable way. Now, let's talk about how to simplify ratios. One key tip is to make sure the numerator and denominator are in the same units. If they're not, it's often easier to convert everything to the smaller unit first. For example, if you have 3 centimeters over 12 meters, converting 12 meters to centimeters makes things simpler. Since 1 meter equals 100 centimeters, 12 meters becomes 1200 centimeters. So, 3 centimeters over 1200 centimeters simplifies to 1 over 400. And of course, if the units are already the same, then you don't need to do any converting. That's a nice shortcut. Like in the example of 2 grams over 8 grams, since they're both in grams, you can directly simplify to 1 over 4. Another example is 2 kilograms over 15 grams. Since 1 kilogram equals 1,000 grams, 2 kilograms becomes 2,000 grams. Now, the ratio is 2,000 grams over 15 grams, which simplifies to 400 over 3. Finally, consider 5 feet over 70 inches. Since 1 foot equals 12 inches, we multiply 5 by 12 to convert it to inches, giving us 60 inches. So the ratio becomes 60 inches over 70 inches, which simplifies to 6 over 7. The main takeaway here is that converting units to the same measurement makes ratios much easier to work with, especially when dealing with decimals. It streamlines the process and helps you see the ratio more clearly. So let's take a look at some more examples. Here, I want to highlight how these concepts we've discussed can be applied in different contexts. Each example demonstrates key principles in action, helping to solidify your understanding. By examining these, you'll see how versatile and adaptable these ideas are across various situations. Remember, the goal is to connect theory to practice, making everything more tangible and relevant to your own work. So, let's explore these examples together and see how they reinforce the overall message of the presentation. All right, let's move on to proportions. So what exactly is a proportion? Well, a proportion is simply an equation that states 2 ratios are equal. For example, if we look at the ratio of dogs to cats earlier, it was 3 to 2. Now, if we compare that to the new ratio, which is 6 to 4, you'll notice that it simplifies back down to 3 to 2. This shows that the 2 ratios are proportional. So when we set up a proportion, we're essentially showing that 2 ratios are equivalent. This concept is really important because it helps us understand and compare different parts of a whole, which ties into the bigger picture of understanding relationships between quantities. All right, let's talk about the properties of a proportion, specifically the cross-product property. So, imagine you have 2 ratios that are equal, like 3 over 4 equals 2 over 6. Now, the cross-product property tells us that if these ratios are truly equal, then the cross products must also be equal. In this case, we multiply across diagonally, 3 times 6, which equals 18, and then 2 times 4, which also equals 8. Wait, that doesn't seem right. Actually, the key point here is that when the ratios are equal, the product of the numerator of the first ratio and the denominator of the second ratio will be the same as the product of the denominator of the first ratio and the numerator of the second ratio. So, for 3 over 4 and 2 over 6, the cross products are 3 times 6 and 2 times 4. And if those are equal, it confirms the ratios form a proportion. This property is a powerful tool because it allows us to verify if 2 ratios are proportional simply by cross-multiplying. Remember, this concept ties back to the overall theme of understanding how ratios and proportions work, helping us solve problems efficiently. Now let's talk about the properties of a proportion, starting with the cross-product property. This is a really useful concept because it helps us understand how proportions work. It states that if 2 ratios are equal, say A over B equals C over D, then the product of the means, which are B and C, is equal to the product of the extremes, A and D in simple terms, add equals BC. This property is essential because it allows us to solve for unknowns in proportions quickly and efficiently. Remember, the key idea here is that when you have a proportion, the product of the extremes equals the product of the means. This helps us confirm whether two ratios form a true proportion or solve for missing values. It's a fundamental concept that ties directly into our overall understanding of ratios and proportions. Let's make sense of the cross-product property. For any numbers of B, C, and D, this property helps us understand when two ratios are equal. Essentially, it tells us that if A over B equals C over D, then the cross products, which are A times D and B times C, must be equal. This is a powerful tool because it allows us to solve proportion problems more easily. Remember, the key idea here is that the equality of ratios is directly connected to the equality of their cross products. This concept is fundamental in understanding proportions and solving related equations, which ties back to our overall goal of mastering proportional reasoning. Let's take a closer look at the reciprocal property of a proportion. So if we have a proportion, can you see what happens if we swap the means or the extremes? Now, if you answered yes, then think about why this works. Essentially, the reciprocal property tells us that a proportion remains true even when we take the reciprocals of the numbers involved. This is a powerful concept because it gives us flexibility in solving proportions. It highlights how the relationships between the numbers stay consistent, regardless of how we manipulate them, which ties back into our overall theme of understanding the properties that make proportions so useful in math. All right, let's work through an example to see how this works in practice. We want to solve for x in the equation. 7 times 6 equals 2 times x. So we start with 7 times 6, which gives us 42. And that's equal to 2x. Next, to isolate x, we divide both sides by 2. Dividing 42 by 2, we get 21. And that's our solution for x. This is a perfect example of the cross-product property, which is really useful when dealing with proportions or equations involving fractions. The key takeaway here is that whatever you do to one side of the equation, you must do to the other side to keep it balanced. In this case, dividing both sides by 2 allowed us to solve for x efficiently. This process highlights the importance of understanding the properties we can apply to simplify equations and find solutions. All right, let's look at another example to reinforce our understanding. We're asked to solve for x in this equation. 7x equals 2 times 12. First, we write it out as 7x equals 24. Now, to isolate x, we can use the cross-product property because we're dealing with a multiplication and an equation. But here's a good question. Can we use the reciprocal property instead? And if we can, would that make things easier? It's worth considering because sometimes different properties can simplify the process. Remember, the key is to choose the most straightforward method to find our solution efficiently. This example highlights how understanding multiple properties gives us flexible strategies for solving equations, which ties back to our overall goal of mastering algebraic techniques. All right, let's take a look at this problem and see if we can solve for. The question is, can you solve this one? We need to find the value of that satisfies the equation. First, notice the original equation. 7x equals x minus 1 times 3. Our goal is to isolate on one side. So the first step is to distribute the 3 on the right side, which gives us 3x minus 3. Now the equation becomes 7x equals 3x minus 3. To gather all the x terms on one side, we'll subtract 3x from both sides. That simplifies to 4x equals minus 3. Next, to solve for x, we divide both sides by 4, which is the coefficient of x, so x equals negative 3 divided by 4. And there you have it, x equals negative 3/4. Now, looking at how we got here, notice the mention of the cross-product property. That's usually used when dealing with proportions or equations involving fractions, but in this case, we didn't use it directly. Instead, we applied the reciprocal property, which involves multiplying or dividing both sides by the same number to solve for the variable. Here, dividing both sides by 4 is a key step. So always remember, when solving equations like this, Look for opportunities to use properties like the cross product or reciprocal property as tools to simplify and isolate your variable. This approach keeps your solutions clear and systematic. Now that we've covered properties, let's put that knowledge to work and solve these mysterious problems. Suppose your car gets 30 miles per gallon. How many gallons of gas would you need to get to school and back every day? Well, you travel 5 miles to home and 5 miles to school, so a total of 10 miles daily. Let's call the number of gallons needed for one day. Can you see how to set this up? Since your car gets 30 miles per gallon and you're traveling 10 miles, then x equals 10 divided by 30. So x equals 1/3 of a gallon per day. Now, how much gas do you use in a week? Let's define T as the total gallons needed for a week. Here, where the properties come into play, multiplying a fraction by the number of days. You use 1 3-gallon each day, so in a week, 7 days, you multiply 1 3 by 7. That gives us 7 3-gallons, which is approximately 2.33 gallons. But wait, earlier I mentioned 5 3-gallons. That's for a different calculation, but here, for a full week, it's 7 3-gallons. Now, if gas costs $3.69 per gallon, how much would that be for the week? Let's call S the total cost for a week. We multiply the total gallons by the price per gallon, 3.69 times 7.3. Doing the math, 3.69 times 7.3 equals about $8.61. So, in summary, knowing the properties helps us break down these problems step by step. And applying the same principles, we can solve real-life questions like this efficiently and accurately. So, what do you think? We've talked about traveling 5 miles to school, and it costs you about $6 a week just for that. Now, imagine if we add in the weekends. If you're driving twice as much on the weekends, say 10 miles to the mall and 10 miles back, how does that change things? Well, first, the total miles you're driving now increases. You'll need more gallons of fuel, obviously. So, how many gallons would you need for this extra distance? And then, what's the total cost? Think about it this way. If you're traveling more, your expenses grow proportionally. So, if you double the miles, you double the fuel and the cost. And when you consider a whole month, these small weekly increases add up. The key concept here is proportions, understanding how changes in distance impact fuel consumption and costs. It's all about seeing the bigger picture and applying these proportional relationships to real-life situations. That's how we can better understand and manage our transportation expenses.